Hello everyone and welcome to this first lecture for an introduction to inorganic chemistry, and this is being followed then by first year chemistry students and as part of the SE 4031 module, and also first year chemical engineering students as part of the SE 4007 module. So hopefully by now you've had a look on the Moodle spaces, you are clear about what is expected of you in terms of assessment. And then this first lecture forms the first part of asynchronous online study for this module, which you can find delineated by week on the Moodle space. So a couple of learning objectives today. I want you, by the end of this session, to be able to draw Lewis structures for a range of molecules and ions, and then finally predict the shapes of molecules using VSEPR theory. Now, a lot of this stuff will be familiar to you from perhaps A-level chemistry or any further study that you've undertaken in chemistry. Nevertheless, these are important concepts and principles, and we must go over them before we can start developing our understanding of molecules and assemblies of atoms that are far more complex than simple molecules or ions. So a good place to start this, and hopefully a little bit of a memory rejog for most of you. So as chemists, we understand about electrons in atoms. We can use the Aufbau principle to give the ground state electron configurations for atoms. And we know and understand about the order of occupation of those atomic orbitals in terms of electron count. And we understand that that follows a certain order. And that order is shown there: 1s, 2s, 2p, 3p, 3s, 3p, 4s, 3d, 4p, and so on. And we also know that each one of those orbitals accommodates 2 electrons. So if we have 3 p orbitals in a p subshell, we know that that can accommodate 6 electrons. If we have 5 d orbitals in a d subshell, we know that that can accommodate 10 electrons. And there I show you, just as a memory jog, the ground state configurations for the first 5 elements, so hydrogen through to boron. Now, we can use some of these principles, some of these ideas about how electrons fill atoms to understand something about their molecular structure. And of course, it's very important that we as chemists understand something about molecular structure, because it dictates so many different things. It dictates the chemical and physical properties of a compound and tells us it's something about its reactivity and how it might behave in the presence of other relevant molecules or ions. So we know then a very basic description of a covalent bond is when neighbouring atoms share electron pairs. So at probably the most simple level you can think of when describing a covalent bond, a single bond is obtained if neighbouring atoms share an electron pair. A double bond is obtained if neighbouring atoms share 2 electron pairs, and indeed a triple bond is obtained if neighbouring atoms share 3 electron pairs. But there are other kinds of electron pairs as well, and we can have unshared valence electrons. And we're really talking about, when thinking about molecular structure and predicting shape, and we'll move on to this idea of a Lewis structure in a moment, we're really thinking about pairs of electrons here. We can also have unshared pairs of electrons, and we call them lone pairs. And a classic example of that is ammonia, NH3, that has a lone pair that sits on top of the nitrogen and the hydrogen atoms in the plane below. Now, these lone pairs, they don't get involved in the bonding of that molecule, but they do exert an important influence on molecular shape. And we'll see this as we move on through to our discussions of VSEPR theory towards the end of this session. So you'll see that in ammonia, that very large lone pair on the top of the nitrogen there forces those hydrogen molecules to adopt the configuration that you see there. And so you can start to understand the effect or the impact that these lone pairs of electrons may have on molecular shape. And if they impact molecular shape, then they also have an influence over molecular properties and will dictate the chemical and physical properties that an atom or an ion exhibits. Now, you'll remember something called the octet rule probably from your studies at maybe GCSE, certainly A level. And you may remember that atoms like to share electrons in order to achieve a total of 8 valence electrons, or what we call a full octet. And we can compare that to something akin to a closed shell noble gas configuration. So something like neon, right at the far right-hand side of the periodic table, has 8 electrons in its s and p orbitals, and we say that it's got a complete octet and is therefore a stable species. And this is one of the reasons why the noble gases are indeed noble and fairly unreactive. So what is the octet rule, and how does it relate to Lewis structures? Well, the octet rule gives us a simple way of constructing a Lewis structure. And all a Lewis structure is a diagram that shows the pattern of bonds and lone pairs in a molecule. So it allows us to understand something about the molecular structure of a species, and it also allows us to understand something about its chemical and physical properties. So how do we construct a Lewis structure? Well, we can do so in 5 simple steps. The first thing we need to do is to add all of the valence electrons that are provided by the atoms within the molecule. And the rule dictates that each atom will provide all of its valence electrons here. So let's have a look at water, H2O. Well, hydrogen contributes or provides 1 electron because it has an electronic configuration of 1s1. Oxygen has its valence electrons in the 2s and 2p shells, and its electron configuration is 2s2, 2p4, so it provides 6 electrons. We add all of those together, so we multiply the 1 by 2 because we've got 2 hydrogens, and we add those 6 valence electrons from oxygen, and we've got 8 valence electrons. So another example here of adding all of those valence electrons. Here is the Cn- anion. Carbon then provides 4 valence electrons. Nitrogen provides 5 valence electrons. We add those two together, but here you'll notice a slight difference. I've added an extra electron here because I'm dealing with an anion. So there's negative charge associated with this ion, so I know there's an extra electron in there somewhere. So I have to add 1 more electron for an anion. So that brings me to a total of 10 valence electrons. The second step then is to put the least electronegative atom in the center of the molecule. So this is an easy task. If you look at the periodic table and you cast your eyes to the top right where I've got those 2 circles there, fluorine is the most electronegative element in the periodic table, and it's followed by oxygen. And as you move away from fluorine and oxygen atoms, those species become less electronegative. So for example, over on the left hand side, lithium, sodium, potassium, those species have the lowest electronegativities in the periodic table. So you can always work out which is the most electronegative atom in your molecule. So for example, if we look at NO2, we look at the periodic table, we find fluorine, and we realize that nitrogen is further away from fluorine than oxygen. And so we place that at the center of our molecule and put our more electronegative species on the outside, oxygen there. We can do exactly the same with phosphorus trichloride, PCl3. Phosphorus will sit at the center of this molecule, being less electronegative than the chlorine atoms. And interestingly, some Lewis structures will only have two atoms. So for example, hydrochloric acid, HCl. There's a fail-safe method here. You've just got to remember that hydrogen will always go on the outside, on the left of the molecule. The third step in constructing a Lewis structure is to place two electrons between atoms to form a chemical bond. So we know that if we place atoms next to each other in a Lewis structure, they have a chemical bond, so they must be sharing a pair of electrons at least. We know that HCl has 8 valence electrons in its structure, 7 from chlorine and 1 from hydrogen. So we place the first two then between the hydrogen and the chlorine, and that establishes our chemical bond. The fourth step is to complete the octets on the outside atoms. So what I've done here is add the additional 6 electrons in this system around chlorine, and that completes the octet for chlorine. It now has 8 electrons. Where Lewis structures are concerned, there will always be an exception at hydrogen because it only needs 2 valence electrons to complete its S outer shell. So remember that hydrogen does not need the classic full octet. And finally, then, if you have got a slightly more complicated system, the fifth step here is if your central atom doesn't have a complete octet, move electrons from outer atoms to form double or triple bonds. So a good example of that is molecular oxygen, O2. So oxygen brings 6 valence electrons. There are 2 of them, so that gives us 12 valence electrons. We know that we've got to place 2 atoms between the 2 electrons between the 2 oxygen atoms to form a chemical bond. If we were to distribute the remaining valence electrons, we'd only get a full octet for one of the oxygen atoms there. The other oxygen atom would only have 6 electrons. What we do then is we move 2 valence electrons and form a double bond between the 2 oxygens. We're still only using 12 valence electrons there, but now both oxygen atoms have a full octet by nature of the fact that they're sharing 4 electrons or 2 pairs of electrons through the double bond there. Now, these might seem simple, and some people might sit there and say, well, I've done all of this at A level, and I know how to make these Lewis structures. My recommendation is that you keep practicing them. And it's very easy to find examples of Lewis structures through Google and other online sources, and just have a go at them. Find a couple of random molecules every week and see if you can describe their Lewis structures. You can always Google the answers. I will take you through a couple of examples now. Okay, so the first example then is oxygen difluoride, OF2. So we know the first step we've got to do is add all of the valence electrons provided by the atoms in our system. Oxygen brings 6 valence electrons, fluorine brings 7, there are 2 of them. So that brings us up to 20 valence electrons. We know that we've got to place the least electronegative atom in the center. Well, we're dealing with the two most electronegative atoms in the periodic table. Oxygen is less electronegative than fluorine, so we put that in the middle and flank it with two fluorine atoms. We then place 2 electrons between the atoms to form a chemical bond, so you can see the shared pairs in black there. The fourth step is to complete the octets on the outside atoms. And if I do that, I use 16 valence electrons. So I've now got 4 valence electrons left. And finally, I complete the octet on the central atom. So I've now used all 20 valence electrons. Every element or atom in that system has a complete octet. Example 2 then, methane, CH4. Well, carbon brings 4 valence electrons. Hydrogen brings 1, and there are 4 of them. So there are 8 valence electrons in that system. I place the atoms, remembering that this time hydrogen atoms will always go on the outside. I place 2 electrons between the atoms to form a chemical bond. Carbon has a complete octet, and you'll note then that we've used all 8 of those valence electrons, but because we're dealing with hydrogen, hydrogen is happy because it only needs 2, and each hydrogen atom there, by sharing through that chemical bond, has 2 valence electrons. Carbon dioxide then, we can add all of those valence electrons, and when you do that you get a total of 16 valence electrons. We place the least electronegative atom in the center, and that's carbon. And we create the chemical bond by placing 2 electrons between the carbon and oxygen atoms. And we complete the octets on the outside atoms. And you'll note now I've used all 16 valence electrons. So take a look at the molecular structure, or the Lewis structure that I show you on the bottom left there. What I've done is I've adopted the 5th step, and I've moved electrons from the oxygen, solely from the oxygen, to share between the carbon and the oxygen. I've still used all of the valence electrons in the system, but now, by creating a double bond between the carbon and the oxygen, that solution gives a full octet for all atoms in the molecule. Example 4 then, the ammonium ion, NH4+. This is a slightly more interesting one. I add all of the valence electrons in the system. Nitrogen brings 5, hydrogen brings 1. We multiply that by 4. That gives me 9 valence electrons, but you'll notice I've got positive charge associated with this ammonium ion, so there's an electron missing somewhere. So I've got to subtract a valence electron from my overall count, which gives me 8 valence electrons. Now this suddenly starts to look like the solution for methane. I place the least electronegative atom in the center, and remember here that I'm dealing with hydrogen, so it always goes on the outside. And I place 2 electrons between each atom to form a chemical bond. Nitrogen now has a complete octet. Hydrogen, each hydrogen atom there has 2 electrons, so everything is satisfied in that example. Okay, ozone then, example number 5, O3. Well, there are 18 valence electrons in that system. There's only one way of arranging those really, they're all as electronegative as each other. 3 of the same atom, so I'm going to draw them in a straight line. If I place 2 electrons between the atoms to form a chemical bond, and then I start to distribute or complete the octets for the outer atoms, then you'll notice that the central oxygen there does not have a complete octet. So I've got to move a pair of electrons somewhere from either the left or right hand oxygen into the center to create a double bond between two of the oxygen atoms. And of course, when I do that, now each atom there has a complete octet. And you'll learn much more about resonance probably in organic chemistry, but this is an important point. A single Lewis structure is not an adequate description of that molecule. There is not a double bond between two specific oxygen atoms in that structure. In fact, it's probably very rapidly flipping between two states. Or perhaps a more appropriate quantum mechanical description would be what's shown here. And this is an interesting point. If you look at the Lewis structure, and you can draw it in either way with dots or with these lines as I've drawn here, the Lewis structure suggests that those two bonds are very different in character. So there is, if you look at the Lewis structure, you see an oxygen-oxygen single bond and an oxygen-oxygen double bond. And looking at that as a chemist, you'd think, well, those bonds are very different in character. One's a double and one's a single bond. But if you do the mathematics on this, you realize that they have exactly the same bond lengths, if you measure their bond lengths. Now, you'll know from your previous studies in chemistry that a double bond and a single bond have different bond lengths. So we would describe that system through this notion of resonance as having an oxygen-oxygen bond length that is somewhere in between the bond length of a single and a double oxygen-oxygen bond. And as I said, it's very likely that this system is actually a dynamic system, and that single and double bond are perhaps alternating or fluctuating very rapidly. And you can show that resonance, or you can highlight that resonance by drawing the two Lewis structures there and putting a double-headed arrow in between the two structures. That tells the reader that the actual structure of that molecule is somewhere in between the left and right structures shown at the bottom there. Okay, so Lewis structures then tell us something about the arrangement of atoms within a molecule, but they don't really tell us much about the shape of a molecule or ion. And particularly in inorganic and organic chemistry, where we really are looking at how molecules and ions react, and particularly in inorganic chemistry, how they are arranged into giant lattice-like structures to create crystals and assemblies of materials that, of course, we can employ in our everyday lives. Shape is really, really important. Shape is very important in terms of reactivity, how we might predict that a molecule or ion reacts with something else. But it's also really important in terms of how molecules and ions assemble into larger structures. And these Lewis structures are a good way of looking at how atoms are arranged, perhaps in a two-dimensional plane. But as I said, they tell us nothing about shape. They only tell us about patterns of bonds and lone pairs. So they tell us about arrangements and distributions of double bonds and single bonds, and where there are lone pairs on that molecule. They tell us about how the atoms are arranged together, the links between those atoms, but not the actual geometry of that molecule, not the molecular shape. And these are very important when we're considering reactivity. So to show you an example of that, to kind of cement this notion that Lewis structures don't portray the shape of a molecule or ion, take a look at the BF4- ion here. The Lewis structure is shown on the left of the diagram there, and the molecular shape, the true molecular shape of the ion, is shown on the right. It's quite a simple Lewis structure to conduct. There are 32 valence electrons in the system, and all boron and fluorine atoms have complete octets. But if you looked at the Lewis structure, then you would be forgiven for assuming that the BF4- ion has a planar geometry. But of course it doesn't. It actually has a tetrahedral molecular geometry. And that clearly has very important implications for how that molecule will react and the kinds of properties that it will exhibit. Similarly then, you would look at the PF3 molecule, phosphorus trifluoride, and you would assume that it's trigonal planar. But there is actually a lone pair of electrons on the phosphorus there that induces a trigonal pyramidal shape. So this is where the valence shell electron pair repulsion theory comes in, VSEPR theory. And it's always a good starting point to begin here in inorganic chemistry, because it gets people thinking about shapes of molecules. And it's used to rationalize or predict the shapes of molecular species. And it's based on one key assumption, that electron pairs adopt arrangements that minimize repulsions between them. In other words, if you've got a number of electron pairs around a central atom in a molecule, and those electron pairs can be several things, they can be bonds, or they can be lone pairs, they are going to want to get as far away from each other as possible. So they will arrange themselves in efficient configurations or shapes around a central atom in order to minimize repulsion between each electron pair. So another way of saying that is that these regions of enhanced electron density take up positions as far apart as possible. Now, all we mean by regions of enhanced electron density are anywhere where there is a concentrated number of electrons. Now that can be bonding pairs, so electron pairs that are involved in a bond. It can be lone pairs, electron pairs that aren't involved in a bond, for example, as with ammonia, and concentrations of electrons that are associated with multiple bonds, so double or triple bonds. Now, this is an important point because I'm going to show you another fail-safe way here of predicting molecular shape using VSEPR theory, but the name of that shape is determined by the arrangement of atoms, and it is not determined by the arrangement of regions of electron density. But we're going to use the arrangement of electron density in the molecule to predict the shape, but we're going to name the shape by how the atoms are organized. So let me show you an example there. Ammonia, NH3, has 4 electron pairs, or there are 4 regions of electron density in that molecule. 3 of them come from shared electron pairs between nitrogen and hydrogen, so a chemical bond. And two of the that's the other region of electron density, comes from the lone pair that sits on top of the nitrogen. Now, the regions of electron density in that molecule are arranged tetrahedrally. Okay, we say they are disposed tetrahedrally. But one of those regions of electron density is a lone pair. So it's not bonded to it, it's not sharing those electrons with another atom. So the molecule, the shape of the molecule then, is trigonal pyramidal. So even though the arrangement of electrons in that system, the arrangement of electron density in that system would be described as tetrahedral, the molecular shape is given as trigonal pyramidal because one of those regions of enhanced electron density happens to be a lone pair. So this is how we start considering or applying the VSEPR model. We start by determining what's called a basic arrangement. So this is why Lewis structures are important, and I think that this is something that isn't necessarily communicated at A-level. It certainly wasn't communicated through my time at A-level, is that this fundamental stuff is really important to predicting shape and therefore properties and reactivity of molecules. So the first thing we do then is we write a Lewis structure and we identify that central atom. And we know that you'll remember that we stick the least electronegative atom in the middle. And then we count the number of atoms and lone pairs. And we know that if we apply the VSEPR model, the lowest energy is achieved by allowing those regions to be as far apart as possible. So we can identify what we call a basic arrangement. And this arrangement is dictated by the distribution or the disposition of electron pairs. So if we've got two regions of enhanced electron density, then the basic arrangement will be linear. If we have three regions of enhanced electron density, the basic arrangement becomes trigonal planar. 4 regions, tetrahedral. 5 regions, trigonal bipyramidal. 6 regions, octahedral. So let's have a look at some examples. Let's go over an example I showed you a couple of slides ago, BF3. So there's, on the left there is the Lewis structure for BF3. You'll note I've omitted the dots for the bonds there, but they are there. Each atom in that molecule has a complete octet. The basic arrangement there of electron density is trigonal planar. Each location there carries a fluorine atom, so the shape of that molecule is also trigonal planar. Now let's have a look at SO3 2-. This is a molecule that shows resonance, but in each case there are 3 atoms bonded to that central sulfur atom and 1 lone pair of electrons. So this is kind of similar to the ammonia case. The basic arrangement, the arrangement of regions of enhanced electron density around that molecule is tetrahedral, but only 3 of those locations correspond to atomic bonds. The other region of enhanced electron density is a lone pair. So the shape of that molecule is trigonal pyramidal. And we've said then that repulsions within that system lie in a specific order. So repulsions are greatest between lone pairs of electrons, followed by repulsions between lone pairs and a bonding region, and followed by repulsion between a bonding region and a bonding region. Let's have a look at hydrogen cyanide. The top portion of the diagram on the right there shows the Lewis structure. There are two atoms here that are attached to a central carbon atom. The basic arrangement, the distribution of regions of enhanced electron density in this system are linear or is linear, and both of these regions are atomic sites or molecular bonds. So the shape of the molecule then is linear. Water is an interesting one. The central oxygen atom is surrounded by 4 regions of enhanced electron density, 2 of them chemical bonds, 2 of them lone pairs. The basic arrangement you would predict correctly is tetrahedral, but only 2 sites are occupied by a chemical bond between hydrogen and oxygen. So the molecular shape is angular. And the HOH bond angle here is 104.5 degrees. And that's because there's a lot of repulsion between the 2 lone pairs on the oxygen atoms that really force those hydrogen atoms around. And that goes back to the point I made a couple of slides ago, that repulsion here is greatest between lone pair interactions. Methane then, a central carbon atom with 4 hydrogen atoms. The basic arrangement of regions of enhanced electron density there tetrahedral. All 4 sites are atomic, or all 4 sites are molecular bonds. So the molecular shape of methane is also tetrahedral. Xenon trifluoride, ZeXeF4, a very wacky molecule. It has a central xenon atom with 4 fluorine atoms, but 2 lone pairs. There are 6 regions of enhanced electron density here, so a basic arrangement can be described as octahedral, but only 4 of those sites are atomic. So the molecular shape is actually square planar. BRF5. There is a central bromine atom surrounded by 5 fluorine atoms and a lone pair. There are again 6 regions of enhanced electron density there, so you'd describe a basic arrangement as octahedral, but one of those regions of enhanced electron density has a lone pair. So there are only 5 atomic sites. So the molecular shape there is square pyramidal. PCl5, a phosphorus atom surrounded by 5 chlorine atoms. Basic arrangement is trigonal bipyramidal. All of those regions are atomic sites, so there are no lone pairs here. So the molecular shape is also a trigonal bipyramid. SF6, a sulfur atom surrounded by 6 fluorine atoms. No lone pairs there, all sites occupied by a fluorine atom, so the basic and the molecular shape here are octahedral. So I will commence the first session there. Hopefully you have learned that Lewis structures can be used to show the pattern of bonds and lone pairs in a molecule or ion. Lewis structures are very useful for showing the number of links between atoms and molecules, but they don't necessarily tell us about molecular shape. And that VSEPR theory can be used then to predict that molecular shape or molecular geometry.